Hello, ladies and gentlemen. Up until this point, we have been discussing the average velocity of the object, and it is important to note that the average velocity of an object is always in the direction of the displacement of that object. For instance, if you have a positive displacement, you're going to end up with a positive velocity for that object. If there is a negative displacement of the object, you'll end up with a negative average velocity for it. Remember, speed is always positive and is entirely independent of the direction of motion. But velocity has these positive and negative values that indicate the direction that they're moving. Okay? Now, more often than not, we are not so much interested in the average velocity of an object as we are the instantaneous velocity of an object. So the instantaneous velocity. Instantaneous velocity. Okay? Basically what we're thinking is, alright, right at this moment. In fact, this word instantaneous, this snap is actually a little too long to indicate what exactly we mean by an instant in physics. Okay? But you kind of get the idea. What is the velocity right then? Oh, that's a terrible snap, I apologize. Right, hang on, wait, I can do this. Yes, right then, got it, okay? So, now mathematically the way we're going to find this is like so. The instantaneous velocity, you'll notice it's different because there's no little bar on it. This is the instantaneous velocity, not the average velocity, because there's no little bar. Right? And we find this by taking the limit as delta t approaches 0 of our change in position divided by our change in time. Right? So basically, as delta t gets smaller and smaller and smaller, as the interval gets smaller and smaller, we get closer and closer to the instantaneous velocity of an object. Now, we can kind of see these things graphically, and one thing we'll note is that the velocity of an object is not always a constant thing. It can very much be changing, and we'll talk about that in a second. So if we're looking at a velocity versus time chart, okay, the velocity could change in any number of ways, right? Okay, we could have something like this. This is a little more true to life. Now, when we do this, if we want to find the average velocity, we would have to take the average of all of these values, and it would probably be somewhere right along there. This would be the average value given a more accurate velocity versus time graph. Now, we can also do these things based off of a position versus time graph. Remember that in a position versus time graph, we can find the velocity of the object based off of the slope. Now, when we had a shape something like this, we were definitely dealing with the average velocity. And we can see that the average velocity is equal to the instantaneous velocity at any point on a graph like this. Okay? But now, mind you, we're going with a different idea now. Okay? And this different idea has the velocity changing in all kinds of ways. Right? Very smoothly in this case. Now, if we're to find the instantaneous velocity of this object, again, you're taking delta t as smaller and smaller and smaller. And if you've been studying in your calculus classes, you'll find the line that is tangent to the point that you're interested in. So if we want to find the instantaneous velocity at, say, this time right here, we would take the tangent line to that point. Not a bad freehand line, but I can do better, and I will for you some other time. So we would take the slope of this tangent point, right, and that would be the instantaneous velocity in this case. Now, in talking about the change in velocity, you'll notice if you're looking at a position versus time graph like so, you'll see that the velocity is obviously changing. If you follow tangent points all around the graph, you'll see they don't all have the same slope. So this object, as it is undergoing this displacement, is changing its velocity constantly, right? In fact, we'll see it is negative here, 0 here, positive, 0 again, negative again, okay? So this thing is really going back and forth in this case. Now, that change in velocity is what we call acceleration. So acceleration, as you may have guessed, or well, we're starting with the average acceleration, is defined mathematically as the change in the velocity and the change in time, right? It's basically answering the question, how quickly does the velocity of this object change? We can expand this form of the equation to be v2 minus v1 over t2 minus t1. That's using the same subscripts as we started with before. So you'll see this equation looks very much like the velocity equation, except that instead of displacement, we have a change in velocity here. But it's still a rate. It's still saying how much it is changing at any one time. Okay? These are equations that you should have by you always because you are going to reference them quite frequently. Now, what we'll notice for this when we take a look at the units here is that the units tell us something about acceleration. Okay, so supposing that we have something whose average acceleration is, we'll say 15, well 15 what? Let's take a look at our units. If we have velocity on top, which in the SI system is normally measured as meters per second, and we have time on the bottom, which is normally measured as seconds, we get meters per second per second. All right, so this acceleration, the average acceleration, is going to be 15 meters per second per second. Now, what we mean by that is that at t1, all right, we'll say t1 is 1 second after the object starts from rest, as we call it, right? At t1, if it starts from rest after 1 second, its velocity is changed by 15 meters per second. So its new velocity would be positive 15 meters per second. If t2 is 1 second later, well, it's added another 15 meters a second to its velocity because its velocity changes 15 meters per second each second. So it would be now traveling at 30 meters per second. 1 second later, it would have added another 15 meters per second of velocity to itself, so it would be traveling at 45 meters per second. I just realized now that I have mixed up my variables here. Let's change that by just adding some big V's. Nope, not capital V's, those would be volume. These are big lowercase v's for the velocity at t1. Velocity at t2 and velocity at t3. Just saved myself. Okay, so this is what we mean by velocity. 15 meters per second means that the velocity changes 15 meters per second every second. Now, normally we don't write it like this. Normally we would write it as 15 meters per second squared. And that's mostly just a space-saving characteristic that we use for it. Right, meters per second squared. But the idea is this one here, meters per second, okay? So, wanted you to see that, I wanted you to experience that. Now, The velocity could change in a positive way or a negative way. It really doesn't matter, okay?